Welcome, everyone. We have lesson 3 coming at you. Just wanted to jump on early to give folks a chance to join the stream. I see that it's, so many people are already here, right? By that, I mean 0. But it's okay. I know that,
We're
you're all
5
just,
minutes early, so,
yeah.
they're just on time. It's all good. Uh,
No early birds here to get the worm, I guess. No, I'm just kidding.
um,
Just hydrating. Good thing. You guys should keep hydrated. Oh, one person joined. Cheers
Look
to
at
you.
that.
Keeping hydrated with water. Thanks for coming. Just gonna hang out. Ooh, maybe we could I don't know, ask questions. I don't know. How are you
Yeah.
doing today? Viewers
Uh,
and David?
oh, hey. I didn't know who you were asking.
I also realized I didn't know who I was asking, so it was a mutual thing. How are you doing today, David? Start with
I'm
you.
I'm doing well. Yeah, it's a little bit rainy here, which is slightly like I haven't really been outside because it's kind of like 40 something degrees Fahrenheit for those of you who are not in and raining, and it's like that's just kind of like I don't know. I don't like cold rain. Like that's not my that's
I would,
probably my least favorite.
I would really like to meet someone that likes cold rain because I feel I feel like that's literally the worst weather in my
Yeah.
I feel like that's like a mutual, we can all agree, cold rain
Yeah,
is
like
not
I'm
enjoyable.
totally fine like walking in like a nice summer rain or something like that, but yeah,
Yeah.
like
It chills you to the bone and like
yeah,
getting soaked like that. Yeah, it stinks. I
not the best.
surprisingly in PA, which, this holds with our theory, just saying. Um, of course, it is sunny today, and it's for whatever reason always only sunny, it seems, whenever I stream on Thursdays for this stream. So it holds. It holds.
Clearly you have me to thank for that. I think
Thank you, David.
it's for scheduling this stream at this time. I mean, like that's I got that right for you, not for
Or
me.
yeah. Or is it that you just wanted me to be so sad because I'm like seeing the sunshine and I can't go.
Can't go
I can't
outside.
go outside and
Sorry,
see
I
it.
apologize.
I'm kidding. I'm kidding. So funny.
Um,
Yeah.
cool. Well, I think let me put this up. I think we'll have this up as we as people begin to arrive. I know you're excited about this
I
to
love
get
the
to talk a little bit.
expanse.
Yeah. So um I don't know like my so I you want to explain what the expanse is, Miranda?
I mean, in my opinion, I feel like The Expanse. Okay, this is a hot take, and some of you might be upset by this, but I think that it's one of the best sci-fi shows that I've seen since Star Trek. So that's my opinion. I don't know. I just love like the world building is excellent. I guess I should start off by saying it is a sci-fi series
Yeah.
based off of a book, and
Yeah.
supposedly, someone can
Series
prove
of
me
books.
wrong here, but I heard that it also may have started as a D&D campaign, which I really wanna play that D&D campaign. I don't know if that's true, but it sounds amazing.
Yeah.
And, yeah, I think it's on Amazon. The show is on Amazon Prime if you wanna check it out, and I've heard the book is excellent. And David, you're reading the book right now, right?
Yeah, I'm reading some of the books. They're fun. Anyway, I feel like actually since we are starting, let's introduce ourselves so that people know who we are. This
That's
is
true.
not an expanse stream. This is
As much as
I'm
I want
David.
that, but, it's
Uh, I'm heading up engineering education here at Timescale. And Miranda is one of the developer advocates here, and she is so this is part of our series of things that we're doing, courses that we're streaming that are actually kind of internal courses, but we want to also let other folks have them and see them because we figure why not? We're already developing the material. May as well let other folks see it too. And Miranda's, I really appreciate her being here. She's sort of stepping in for the audience today. So if you have questions, she's going to help ask them, and please put them in the chat, and we'll try to see if we can answer them. She's going to help sort of serve as that proxy as well, which is really great. So and we were just talking about the expanse because this is, I like to have something as we're sort of waiting for the first couple minutes as people arrive to talk about. And today, what I was thinking about are side, like as I was reading this, right? So much like Miranda, I learned about this relatively recently, and I binged the whole show a little while ago. Bad, but whatever. And then I'm reading some of the books, and I thought the story was great. And I was thinking about sci-fi explanations of things, right? And specifically, I was thinking about the Epstein drive. This guy saw like and the sci-fi explanation for that, right? So this comes from. By the way, I had like this is the show and the books. But when we're thinking about like the sci-fi explanation for something like this, right? Like just sort of what they provide and what they don't. Right, like so the Epstein drive is like really efficient, and it was developed by this guy Solomon Epstein because he like was tweaking things with his fusion drive, and like we don't really know exactly what he tweaked or what happened, but we know that it worked better. Like it was so much more efficient than any drive that had been before, and it like completely changed how the people were able to travel throughout the solar system. So like that's a sci-fi explanation, right? We don't get actually how it worked, but we get what it affected and how it changed things, or like, and there's enough of an explanation that like it's like, okay, I kind of get maybe what happened there. I also think it's like kind of like actually so many science things have happened with some accidental thing, and like the whole explanation of like he made this mistake and then he got shot out of the solar system and like is now the furthest thing from the solar system, and is like going at a pace that's approaching the speed of light because his drive is just accelerating forever. But luckily, like all of the plans and all the things that he did were like beamed back to Earth and were on his wife's computer, and like like so many scientific accidents kind of happen that way. It's just kind of fun. Anyway, uh thinking like penicillin, but so this type of sci-fi explanation though, right? Like this sort of like,
Oh, and we get an
right?
Obi-Wan Kenobi quote.
Yeah, like
Wow.
this is the original explanation of the Force. And sometimes when sci-fi tries to do a little bit more than that, it gets a little weird, right? Like it's like, oh god, now we could start talking about midichlorians, right? um
Not the midichlorians. No.
So I'm going to try and avoid that, because it turns out the difference between sci-fi and real stuff is that you can actually explain some of it and maybe make some sense of it. And part of the reason I bring this up though is because we're going to be talking about indexes today, and I feel like people have sort of a sci-fi understanding of indexes to an extent. We're like, oh, they're cool. So we're going to start with that sci-fi explanation, sort of what they do, how they help, all of that stuff, and then we're going to go into a little bit more of how they actually work. So that's my goal this time. I want to have a little disclaimer here. We have over the past 3 lessons. This is the 4th lesson. We started with lesson 0. Zero indexing still screws me up sometimes, but so this is the 4th lesson. We are going to go a little bit more advanced from here on out. We're going to go at a bit of a different pace. This may be a little bit of a pace change for some people who were who joined us at the beginning. There are a few reasons that we're doing that. One of the main ones is that this is actually an internal course, right? As I was just saying, that is meant for helping onboard engineers who may have different backgrounds and not know as much about databases. And so we want to go a bit fast. We've had some requests for that, both from users and from engineers. And so I want to sort of cater to that want, as well as like I just think that I'm going to be better at that, frankly. And there are a lot of courses that cover the basics of SQL. So if you're looking for the pure like SQL basics, going over lots of commands and some of the things that you can do, like great time to pause, go do some of that, come back, and we'll get into a little bit deeper understanding. So I just wanted to mention that before we go on today. And but please do ask questions still. Like there's the possibility I'll say I can't answer that right now, or I'm going to answer it a little later, or like just can't get into it. But most of the time, I'm really going to try and answer it and help you through. So, okay, so let's get into that sci-fi explanation. So what do indexes do? And basically, there are two things. One, we want to make queries faster. And two, we want to enforce constraints. So and we'll get into each of them separately. So what do indexes do? Making queries faster. So how do they do that? And in order to actually understand what's happening here, we're going to read a little bit of an explain plan. Now, we'll do a whole lesson on explain at some point. So we're going to give some of the stuff that you need to know about it now, and then we're probably going to do some more stuff around that a little later. So essentially, an explain plan is a way of asking the database to tell us how it does something under the hood. So when I say I want this, like select X from Y where Z, what is it actually doing to give me that result? We're going to do this, do a brief interlude on it. So first off, you have the command that we run. So we say we just add this in front of our query, and it's going to give us this query plan as an output. And that query plan also gives us some timings because we use this analyze parameter, which says, I want you to actually run the query and figure out what's going on there. And so it gives us some planning time and execution time. We won't talk about exactly the differences between planning and execution time for now. It also tells us something about how it did the work. So in this case, we were talking about indexes. We got an index scan. Hey, that's nice. That's what we wanted. Now, I want to talk briefly about this buffers thing. So this is one of the things that may be a little bit more foreign to folks if maybe you know a bit about explain or even explain analyze, but explain analyze buffers might be more foreign. I love explain analyze buffers. And you'll see that we can actually see differences in timing as we start looking at the way that these buffers are hit. And what I want to explain here is this is what we're talking about. If you remember back in lesson 0, when we were talking about the architecture of a computer, and we said, okay, remember that things are going to be read from storage into memory, and then from memory into the CPU where they get processed and worked on. So that memory is also known as the buffers or a cache. Right. So you'll see that some of the stuff is either in the disk cache or in actual shared memory that Postgres is managing. And we have to remember that memory is much faster than the storage. And you can see the difference here, right? So when we look at the number of buffers that we see that the first one hits 4 and it's taking 53 microseconds. And so when it says hit, it means that's what's actually in memory. When it says read down below, here, right? So it says it hit 2 and it read 2. It means it actually had to go to disk for 2 out of the 4 buffers that it's reading. And we can see the difference in the in the timings there, right? Because it had to read 2 of those buffers rather than getting them straight from memory, it took actually a lot longer. So that's one thing that we are looking for. This is also an explanation, right? When you run queries multiple times with explain or otherwise, they get faster. It's because more of those buffers are in shared memory. So that's just a thing that we should know about. And remember also that when it says 2 and 4, right? What we're talking about here is a block or a page in the file system, and Postgres almost always uses 8 kilobyte pages. So when it says we're reading 4 8 kilobyte pages, which fit more than one row, and you'll see that they actually will, when we look at it later, they actually have many rows on it. Okay, so we understand now a little bit more about how the buffers part works, and how when we have to read more pages, that's going to take longer. We can also see that if now we can use this to understand how indexes are making queries faster, right? A little bit about that, right? So I made a separate schema, right? If you remember what schemas are, right? We were doing that schema notation last time. So And I call that one Postgres error no index. And that's one where I've just essentially restored the data, but I haven't restored any of the indexes. So that it's like, okay, I can do this, but not have the indexes there. And so if we look at what's going on there, it's now doing a sequential scan rather than an index scan. So it's reading the whole table. You'll also see that it's hitting a lot more buffers. Now, it happened to hit all of those, so it didn't need to read. But you'll see and by the way, so the index first off is allowing us to go straight to the specific account ID. So you can't quite see this on here, but the account ID that I have over here, if you could see it, is actually a different account ID. Oh no, I think it's the same account ID in this case. By the way, just to let you know, when I did this one where we were like reading to, you'll notice that I just changed the account ID here, and that let me see something that was not in buffers. Anyway, but over here, as I'm doing this, it's the same account ID. We're reading it, reading the same one, and as I'm doing it, what's actually happening is we're reading all of the rows. And I'm just applying this filter, which means I read the rows and I look for the account ID. As if it's 24, then I return it, and if not, I keep going. And you'll see that we removed 257,332 rows from the that I read. So I had to read all of those. They're on about 2,687 pages, right? So we're looking at something like 10,000 pages per row, or 10,000 rows per page, excuse me. Got that backwards. That would be weird. Very big rows. And you can see also that these are all in shared buffers here. So this is like, we're not dealing with differing times in terms of reads. We're just dealing with the number of pages we have to look at in terms of the differences in timing here. And you can see that correlates basically to our difference in timing. It's about 500 times more pages that we hit, and it's about 500 times in terms of the timing, approximately. Right? Order of magnitude estimation there. So that's a useful thing to know. The way that an index is helping us is it's getting us to this filter that we have, the where clause. We don't need to scan all the rows to do it. We can actually just use the index condition. It tells us that the where clause is fulfilled. So we can go straight to that row instead of having to scan through a lot of them to get there. So that's how an index is making our queries faster. The other thing, this is just a sidebar here. When I actually first did this, I got parallel scans, which is another way that Postgres tries to speed up queries. And so I got a parallel sequential scan rather than a normal sequential scan. And in order to get rid of that, I had to set these parameters so that I could just get a normal sequential scan. And let's remember also just one other thing, sequential scan. This is just something to remind yourself of, right? It is usually faster than when you're reading from disk than an index scan in some cases, because index scans are a little bit more random access. And we'll go and get in maybe into why that is, but the reason it's called a sequential scan is because we're actually reading the blocks on the disk in an order, which means that's usually a little faster way to read things. Okay, so we looked at how this changed the execution time, and the whole goal here, the first sci-fi explanation was, hey, look, we can see that the index made the query faster. That's nice. 500 times faster in this case, right? And of course, this doesn't matter, right? Like, this amount of timing doesn't matter. It's still like under the threshold of being like comprehensible by a human being, really. But as you get to much larger data volumes, this starts to matter a lot more. So then our next thing that indexes do is they can enforce unique constraints. So let's talk a little bit about enforcing constraints. We looked at that describe our accounts table that we were looking at last time. Okay, wait, what are constraints again? So let's think about what constraints are, and then we'll talk about how indexes help us enforce them. Constraints essentially are invariants, something that the database enforces. So you say, if something is true, you allow the operation, otherwise we're going to throw an error. And they're usually enforced during the data modification step, so like insert, update, or delete. but they're created during the data definition step. So it's a way of telling the database what we want it to do. Now, why would I have these? Well, a database is a shared state. Multiple applications are going to be using the database. If I have to, the database is a good place then to store the shared assumptions that we want to have as invariants across those different applications, so that then I don't have to go and audit the code of some other program to say like, hey, are you assuming the same things that I am? No, the database can enforce that, and our DDL can tell us what's going on there. And so we can start from a shared set of assumptions. So let's look at what that really means here. So one implicit constraint is just the data type of a column, right? So account ID is an integer. If I were to try to, like, if my application decided I want to generate a text ID instead, well, your new application and the old application that was running with integer IDs now would, like, if you just allowed it, well, one of them would have an error. Probably the old one would have an error. But here you can see instead what ends up happening here is we get an error when we try and insert the data. So now we have less of a chance of getting really dirty data, and the database is enforcing the condition. And so you see this type of error where we say, okay, well, we can allow the integer account ID, right? Account ID here in the values, but we can't allow the text account ID. And we see, hey, that's not an integer, the database tells us. Okay, so that's and then of course, as usual, I have slides saying exactly what I said. Great. So, but let's go in and let's focus on the login column for now. So one other constraint that it has is a not null constraint. And a not null constraint, you may remember from last time, this is somewhat review, right? That this is saying this needs to exist. Right? We need to have something here. So null is an unknown, or it's like a value saying we don't know what this thing is. There are some columns that we say we can't allow that for. We need a login email in this case. And so if I try and say put in a null value, I will get an error. So right, we have our foobar at timescale.com account, which is of course for our favorite employee, Mr. Foo, or Mr. Bar, I guess, or Ms. Bar. I don't know. But if I try and do this, I'm just going to get this error, and it's going to say, well, that violates my not null constraint. And so, okay, so then I was like, okay, well, maybe it would be fun to try and enforce that that in fact login is a valid email. That was sort of my next thing, is like maybe we can add a constraint that would do something like that, and we would use something called a check constraint for that. But then I was like, oh man, validating an email is actually really hard, because emails are weird, and like there's a whole specification for the characters that are allowed and the order they're allowed in and what emails are equal and all sorts of other fun craziness. And so if you actually wanted to do this, this is what you would do apparently. And by the way, this is also me telling you, and I wanted to have this interlude here because, like, yes, I go and look at Stack Exchange for this stuff too. Everyone does. It's okay, especially when you're dealing with.
Everyone uses Stack Exchange.
Yeah, like, please feel free.
And Stack Overflow.
Yes, and like, so this is one way to validate an email, and oh God, I have no idea what's actually really going on there, but I'm going to assume it's right because someone else tested it to an extent. Also, this is not my main job here, and I'd already spent an hour on it, and I was like, okay, I need to stop. The other thing that I noticed is that it turns out when we try and add this check constraint to our table, it fails. Because it turns out there are some invalid emails in our demo data, which is totally fair. There's some spaces, is basically what I found when I looked into this a little bit more. Can't have spaces in emails, it turns out. So this would be a reason to have this type of constraint, is that then you wouldn't have dirty data. But it also shows you what would happen if we were to try and add a constraint that was not valid, right? It's going to error in a similar way. Um, and so anyway, you can add this thing called a check constraint. It is also like, it's basically saying apply this function to things in this row. I can have multiple columns in the same row. That's nice, but this is a tangent. All of these constraints, the thing that we need to recognize here is that these are all constraints on a per row basis. And the thing about indexes that is cool is that they're what allow constraints across multiple rows. Right? So all of the data type stuff, we're just sort of dealing with that row when we do something. But indexes are saying, hey, I want this like this to be unique. So only one of this email can go in to the table, and I'm going to enforce that. And if I have another version of that email, right, I don't want to have that. So one way that you could enforce that would be to say, well, hey, why doesn't my application just select first and then insert if it doesn't exist? Well, the answer is, well, everyone's application? What if someone decides to add it by hand? What if someone writes a different application that forgets to do the select first? What if there's a bug, right? So enforcing this in the database really makes sure that you can assume that it is unique and doesn't cause weird bugs when, like, you look up the email and it turns out it's not unique. Now, there are other things you'd want to consider with email, by the way. You'd want to actually normalize your email first, too, probably, so that, like, because sometimes capitalization doesn't matter, for instance, and other sorts of stuff. So you'd probably want to do that to make sure that you're actually being unique. But, again, emails are horrible. Okay, so we might add a constraint saying we want to add this unique constraint. And you'll notice that as soon as I do that, one, we can still do this type of checking that the constraint is valid, right? So if we try to add two rows that have the same email address, the same login, we get this error saying that there's a duplicate key. Great. So that's on the whole table. And you'll note that this added an index. So when we look at our describe PostgreSQL again, we see that now there is this new index here for this unique constraint. So we sort of saw that we wanted to we got to the point where we're like, okay, this is the sci-fi explanation. We got the making queries faster. We're enforcing constraints. So now we want to know, how do indexes do this, right? And the answer here is actually kind of in that text. It's a B tree. And so now we're sort of getting, and we're going to get a little bit into this. This is our next section here. So we've already gone a little bit past the sci-fi explanations, but now we're going to get more into the weeds. So as I do that, we're going to like really get into some internal structure, understand what they're best at, and try to figure out then how we can use them better. Is the goal. We're not going to get to all of that this time, but we're probably going to have 2 or 3 of these sort of lectures on indexes, especially B-tree indexes, because they're not the only type in Postgres. We may do some other things on other index types at some point, but we'll see. Okay, so with that, before we go on to that, are there any questions? People following? I don't know. Miranda,
Oh,
how about you?
there, there's a question. Hi, can I use MongoDB instead of Postgres? Yes, you can. Depends on what you need the database for.
Yeah.
I would say.
And I mean, right now we're like, so I don't know if Mongo does like explains like this. I don't know. It has indexing as well. I think it's probably using some sort of tree structure. I don't know exactly the structures that it's using there. It's more of a key value store, and that's like a different kind of thing. But yeah, that's yeah. Anyway, so let's go on and try to understand a little bit about B trees, and then we'll sort of go from there. So this is kind of what a B tree looks like. Obviously not in real life, but it is, this is a visual representation of that. that can be a bit overwhelming. So let's start with how we might use a structure like that. And so how could I find a particular piece of information? Say I wanted to find, like we said in that query back there, ID 24, account ID 24. So how do we look for 24 in this B tree to see if it exists or if it doesn't or whatever else? So we start at the root node, and we go from there and we say, okay, here's where we're going to start. We'll start at the top. I then look at 32 and 67 and I say, well, 24 is less than 32. So I'm going to follow it over to the left. And then I find, okay, so this tells me, hey, 24 is between 20 and 27. So I need to follow the pointer between 20 and 27 and go to this, what we're calling what's called a leaf node. So this is where maybe the data is stored. And I'm going to find, hey, 24 isn't actually there, which is fine. That actually tells us a lot, right? Like it would be much worse if we had scanned all of the data in the table only to find the 24 isn't there, first off. This also tells us a little bit about what would happen, right? Like if we're enforcing a unique constraint, if it's there, then we block. And if it isn't, then we can add it in. And we've returned, but either way, we're returning having scanned only a small number of index pages rather than having to scan the whole table. Okay, so maybe we're looking to insert the data. What we do here, well, there's room on this leaf page, so we're just going to add it in there. And now what I'm not going to do is go into all of the balancing that then needs to happen on insert. There's a lot of stuff in the internals of this algorithm that tell us how we balance pages and what we have to do in order to go back up the tree in order to make sure that inserts work and all sorts of other stuff that I'm honestly not going to get into here because it's not actually like that's important if you are thinking about how you would implement this, but it's less important for using it for the most part. So yeah, so we're not going to deal with page splits and propagating back up the tree and all sorts of other stuff like that. So let's go on. First off, like I said before, if it existed and we were trying to enforce a unique constraint, we would have errored. We're saying, and again, we still only had to scan a small number of pages because you can imagine that if I had to scan the entire table every time I inserted one row, that would be horrible. It would be horrible for performance. I'd have to read everything every time I wanted to add one row in, and that would just be like the performance hit that you would take would be so massive. So technically, what this B tree structure is allowing us to do is, when I say small number of pages, computer scientists like quantify that, and they say it's actually a logarithmic compared to the size of the data set. So we have to scan a much smaller number of pages. Okay, so and let's also quickly go over, right? So when I painted these things purple over here, right, when we were following that path, following these pointers. This also tells us about the types of buffers that we're hitting. This is why we're hitting so few buffers and why we sort of hit a couple of the same buffers when I did the second explain plan. Those are probably the ones at the top of the tree. And because we got a different ID that we were looking for, that's going to be somewhere over there. And that wasn't that one. Those pages had to be read. Whereas the other ones were living in memory. So part of what you're also getting here is that those top pages in the tree are going to be in memory much more of the time. They're often going to sort of live in memory. And so and also I just wanted to explain to you that whenever I'm making this color change, it's really like I'm going to search for that. It also means that I've read it into memory now if it was on disk. Okay. So then what other types of scans are B trees good at? Like what else can we do with them? So you'll note that in these leaf nodes, there's some ordering. So if we had a where clause that was an ordered subset or some range of values, we can actually scan just the way we did down to 24 if that's our starting point. And then we can follow the leaf node pointers in order to get to the next leaf node, which gets us all the way up to 30. And then we can stop. Now, technically, this means that the tree that we're looking at here is technically a B plus or a B star tree. I can't remember exactly which one, but I'm treating all of these as a B tree. So, like the exact technical implementation, I'm not going to go too much into. But essentially, these pointers down here, these arrows that are going between these pages at the leaf nodes, there probably also are ones in these middle nodes as well, right? But all of that means that it's probably technically this subtype of B tree, but just call it a B tree. It's more than enough to know. So the other thing that we could do is something like an order by ID limit n, right? Or even just a normal order by query, right? So if we wanted to order by this thing, we would scan down to the far left node, and then we could follow the leaf node pointers until we reach whatever our limit was. So maybe this was limit 10, so we got to 10 values, and then we can stop. So that's another type of query that a B tree can do. The other thing is it doesn't need to be integers, right? So any type that can be ordered can go into a B tree. In this case, I've chosen a text words. In this case, these are valid two-letter Scrabble words. Not all of them, but these are not all of the valid two-letter Scrabble words. These are a subset of the valid two-letter Scrabble words, but they are all, in fact, valid two-letter Scrabble words because I'm a nerd. Now, so in this type of query, right, I could find something like all the words beginning with B, right? Again, that's an ordered query. Like, so this is something like where word like B percent is a wild card. So in a like clause, so if we want to find all those, we would scan a similar way to we did with integers. And so we'd scan through, and I forgot to color in the root node. Sorry about that. It assumed that it's colored in. We'd scan through, we'd see that B is actually to the left of go, and that it's between ax and by. So all the words starting with B should be between ax and by. And then we get to the page, and we read the BA, ba, B, and by, following the leaf node pointers again, and we would get all of the B words. So again, we have an ordered subset. What that means it doesn't do is it can't help us find, say, all of the words that have B anywhere in the word, right? So it only helps with prefixes, right? So it's going to miss AB, ab, because it doesn't start with B. So it's only helping us find ordered subsets or prefixes if we're talking about words. Okay. So what we want to take away from that, I think, is that what we have in a B tree is a fundamentally an ordered data structure, right? It's helping us understand that ordering and search through that ordering very efficiently for an on-disk data structure. And so now what I want to do is talk a little bit about how B trees are actually different in Postgres, or a little bit different maybe in Postgres than in some other systems. And I also want to make sure we have some time for questions. So let me actually pause before that and ask, how are folks feeling about this? Is this feeling clear? Are you feeling like you kind of get it? Is this overwhelming? How are we doing here?
We had a little discussion, and I think folks are good for right now. Definitely some hopeful,
Yeah,
encouragement for, let's have more Postgres
totally.
content. So
Absolutely. And I think that we will absolutely be working on some of that stuff. And Noman, I think some of the previous lessons should help a little bit more maybe on some of that. I also think that understanding, like, it will not hurt you at all if you're trying to understand Postgres to understand B trees a bit, right? B trees are fundamental to any sort of relational database and really any database. So I think that they are things that you absolutely will benefit from knowing sort of how that works. I would still recommend that you go and, like, just work with Postgres a bit. Try to do some stuff in it. like play around with it, use what we did last time, right? Open up that Postgres Air sort of tutorial, run some queries, try and figure out what's going on, and just struggle a little bit, read the documentation. Like that's often the best way to learn. But it's also kind of frustrating to watch on a stream where someone's supposed to be teaching you. So I think that's something that you're going to have to do on your own a little bit. But I think that hopefully you can do some of that. There's also some resources maybe we can point you to for some of that as well. But hopefully we'll be developing more of that stuff as we go. And it's really great to hear that there's a demand for that because it helps us prioritize what we want to do. So thank you for letting us know. Okay, so B trees fundamentally ordered. Good to know. The next thing that I wanted to cover, and this is really the last thing for today, we are sort of running up on time anyway, is to understand a little bit more about how B trees actually work in Postgres in particular, and maybe what's different about a B tree in Postgres versus a B tree in another database, in at least some other databases. Okay. So let's talk about primary keys and the heap, because I think that that's an important bit here. Okay, so we talked about B tree data structure, and one of the things that you'll note here is that down at the bottom here, what I was sort of skipping over in these leaf nodes, I have this thing data/pointer. PTR is a stand-in for pointer here. Why did I have that? Well, in some databases, and the other thing, by the way, that I wanted to just mention is that a primary key is called a primary key. So does anyone know what the difference is between a primary key and a unique plus a not null constraint? Because a primary
I
key,
know.
like if I put a unique plus a not null constraint on my column, right? It essentially functions like those are the constraints that I'm going to have on it, right? It needs to be unique. It needs to be not null. That's really what a primary key is telling me. It serves as a unique identifier if those two things are true. So then I suppose the question is, what then is the difference here? And the difference in Postgres, that is not true, Andre. Actually, you're close, kind of, but you can in fact have a primary key on multiple columns in Postgres, at least. That may not be true in some other databases. So a multi-column index, multi-column indexes in Postgres can be primary keys. That may not be true in some other databases. And in some databases, there is a difference between a primary key and a unique and not null constraint. And in Postgres, there isn't a difference. So a true primary key, right, where it's serving as the primary data store, means that the data itself is stored in this B tree structure. So like MySQL InnoDB stores the rows inside of the B tree itself. Whereas in Postgres, right? Oh, and by the way, then you have the idea of a secondary index, right? So a unique key or a secondary index is actually going to point back to the primary key, right? So if we switch, if we say, hey, my primary key is my whatever this text column is, right? That's going to store the data in some databases, and my secondary key is going to store pointers back to the primary key so that you can go find the rest of the row. That somewhat clear what the difference is there? Okay, so so one of the things that you should know is all indexes in Postgres are essentially secondary. The primary storage mechanism for Postgres is called the heap, right? And essentially, it is a file with a collection of pages and rows that are stored in that file, and it's called the heap. And so all Postgres indexes actually point back to the heap. So we always have this secondary structure where it's pointing back to the actual row on the disk. Now, if we get too far, and technically it's not actually a pointer, it's something called a TID, or a tuple identifier is the other way you'll hear that called. Right, so TID is a tuple identifier, and technically it's a physical, not a logical identifier. So primary keys in some other data, like the primary key is a logical identifier. It says it uniquely identifies the row itself. The TID is actually where this is only identifying where this row lives on disk. And that, like, if you look at that TID again sometime later, there might be a different row there at some point in the future because some operation happened and things switched places. So in order to really understand all of that, we're starting to get into MVCC, which is multi-version concurrency control and transactionality and all of that stuff. And I think, given the fact that we really only have like 10 minutes left, I can't get into that now. And also, I don't have the slides prepared. So that might be something that we can get into maybe next time. I also want to talk about multi-column indexes and other sorts of stuff like that, because I think those are really important to understand. But I wanted to just like go back and look at one more thing, because you may have noticed that we had to read a couple new pages when we did that scan. That caught, like, those two different index scans, some of which caused us to read, and some of us had to not. We didn't have to read. And so remember that the Postgres index is actually pointing back towards the heap. So while we also probably had to look up another maybe leaf node of the index, we also had to go and find the page in the heap. Now that's easy to do because it's entirely ordered. So that's where we're going to conclude this lesson. I hope that was useful for you. I think I went through this pretty fast, and maybe people have questions, maybe people don't. If you have questions, feel free to ask them now. Otherwise, we can just chat for a bit. But yeah, I hope that was helpful for folks. And we'll be back next time. We'll probably have an index. We'll probably have another one or two index lessons. So yeah, so I'll see if we get some questions here, and would love to go over some of that stuff. Aha.
Okay.
Yeah.
Yes, we have some questions. Sorry, I'm just fixing. I need to fix that link that I sent. My apologies. It added an extra slash on the end there, so I will fix that in the comments. But David, if you can read the questions while I fix that link.
Yeah. Cool. So Fahad asked, when are we getting into TimescaleDB? And so this was actually, if you were here earlier when I mentioned that I'm sort of speeding things up, this was the other reason that I really wanted to do that. So we're already about 4 lessons in, and we haven't yet really gotten to TimescaleDB. Like, indexes to me are one of the main reasons that one of the places where they're really useful to understand um, uh, uh, what's going on with Postgres and indexes. There are a lot of what we're doing in terms of speeding things up is we're still allowing you to use your indexes and use your indexes well. But we're keeping things very efficient in terms of inserts and other sorts of stuff. So we're going to get into my plan for next time. Actually, is hopefully we get to the next session will be in 2 weeks, Fahad. We've been doing them every 2 weeks, and uh, and so we're going to talk about hypertables and indexing and how they interact. That's going to be a large part of what we cover there. And I also want to make sure we get a little bit more of some of the basics of indexing, especially around multi-column indexes, before we start talking about some of that, because I think there's some really good things around indexing. Actually, some of the stuff that Andre is asking about now that I'm planning on covering next time. So I'll definitely use that as sort of a guide to what I should be talking about, Andre. I appreciate that, and I hope I'm pronouncing your name right. but I also will say, first off, one thing to just note here, because you asked a question, I think there's something like a sort of misconception there, maybe. So Postgres, whenever you just use create index without specifying anything else, it creates a B tree index. So if you have a date time column or something like that, technically a date time column is stored as an integer internally, by the way. So it's actually using a very similar structure to what we're talking about here. It is using B trees. Unless you specify a different index type, it is going to use a B tree. B trees are the default index in almost every database um, around. So the other thing is, yes, you can use datetime index as a primary key. I wouldn't usually do that because it only allows you to have one value per time, right? It's a unique key, so you would only have then one value per timestamp. Often we actually use a composite primary key as our primary key on a hypertable, and so that's another thing that we can talk about next time, and why we do that and what's cool about that. So often we have something like so your date time needs to be there, but that'll be a column that we will uh, that'll be one of the columns. It won't be the only column. And we'll talk about column ordering and other sorts of stuff like that. So that's sort of where I plan on getting to next time. So I hope that was useful for you there. And we can sort of go on to more of that and exactly how uniqueness and partitioning and all of that stuff works. So that's some of the stuff that I'm hoping to get to next time. And I think we'll finally on our fifth lesson be getting to Timescale. I didn't want to wait another like 3 months to get there, so I wanted to go a bit fast through this. Yes, I think that that's a great index for you, and I would definitely recommend that you have device ID or whatever first. So that's a spoiler for next time, I guess. But yeah, so next time we'll go into some more of this, and we'll get to actually, like, I guess, build up a bit more of that. There is also the possibility that I will speed up that one and do it next Thursday, not 2 weeks from now, because I'm actually going to be possibly out the following Thursday. I don't want to wait a month. So I'll talk with Miranda and other folks and see if we can maybe do that a week early or something like that. So let's see how that goes, and we'll post on social media and maybe also in the chat on this video or wherever this ends up being fully posted, and let you know if it's going to be next week or the week after. And yeah, so hope that's helpful for y'all. And really appreciate the questions. It was great having you here. And let us know what if there's other stuff that you want covered, please do leave that in the chat. If there's questions that you have from previous things, we're happy to help. So thanks, everyone.